Okay, so let's rewind to 1950. Long before AI was a term you heard every single day, the mathematician Alan Turing published this paper. It was called Computing Machinery and Intelligence. And this thing, it didn't just kickstart the conversation, it basically built the entire stadium where we're all still arguing about artificial intelligence today. So, right at the top, Turing hits us with this huge question, probably the most famous question in all of computer science. Can machines think? It's a question that feels, both super deep and really simple at the same time. It's the puzzle at the heart of everything. But here's the kicker. In the very same paragraph, Turing does something, well, kind of shocking. He completely dismisses his own question. He calls it too meaningless to deserve discussion. So, what's up with that? Why ask this epic question just to immediately shoot it down? All right, so to figure this out, we're going to follow his train of thought. First, we'll see why he tossed out that famous question. Then, we'll get into his brilliant imitation game that he proposed to replace it. We'll watch him take on his own critics, look at his wild ideas for how to actually build a mind, and then we'll wrap up with a prediction he made that is eerily relevant to our world right now. Okay, let's dive into that first part. Why did Turing think asking, "Can machines think?" was just a total trap? Well, for him, it was like stepping into philosophical quicksand. The problem? The words themselves. Machine and think, what do they really mean? He argued that trying to define them would just end in a stalemate. It wouldn't be science, it'd be more like taking a popularity poll. And for a scientist like Turing, that was a total non-starter. So, instead of getting bogged down in endless definitions, Turing came up with this incredibly clever solution. Just replace the question with a game he called the imitation game. And what's so cool is that the game he starts with, well, it has nothing to do with computers at all. Okay, so picture this. You've got three people. There's an interrogator, C, in one room. And in another room, there's a man, A, and a woman, B. The interrogator's job is to figure out which is which, just by asking them questions through typewritten notes. Now, here's the twist. The man's job is to trick the interrogator, and the woman's job is to help the interrogator. And then, this is the genius move. Turing says, okay, let's make one tiny change. What happens if we take out player A, the man whose job is to deceive, and we replace him with a machine? And boom, just like that, the game isn't about identifying gender anymore. It's about figuring out who's the human and who's the machine. You see what he did? He swapped this fuzzy philosophical question for a concrete, measurable test. It's not about what's going on inside the machine's head. Who cares? It's all about performance. Can it imitate a human being so convincingly that it can fool you? And that, right there, is what we all now know as the Turing test. Now, Turing was no fool. He knew people were going to come at him with all sorts of arguments against this idea. So he does something amazing. He basically spends a huge chunk of the paper becoming his own toughest critic, anticipating and shooting down 9 different objections before anyone else could. He takes on objections from theology, from math, from all these ideas about what makes humans special. We're just going to look at a couple of the big ones that people still argue about today. Okay, first up, the argument from consciousness. This is the classic, right? A critic says, sure, a machine can write a sonnet, but it doesn't feel it. It's just faking it. Turing's comeback is just brilliant and kind of brutal. He basically says, hold on, how do you know I'm thinking? The only way to be 100% sure someone else is conscious is to literally be them. We just kind of politely agree that everyone else thinks. So his point is, if a machine is just as convincing, why not give it the same benefit of the doubt? All right, next up is a big one, often called Lady Lovelace's objection. This is the idea that a machine can never be truly original. It can only do what we tell it to do. And Turing's response is so simple and so perfect. He just says, machines take me by surprise with great frequency. His point is that just because you have a set of instructions doesn't mean you can predict everything that will come out of it. Real creativity, real surprise can bubble up from that complexity. And this leads to a really subtle but super important point. To actually pass this test, a machine can't just be smart. It has to be human, flaws and all. He knew that if you asked a machine a hard math problem and it shot back the perfect answer in a nanosecond, well, game over. That's a dead giveaway.
So a really smart machine would have to know how to play dumb. It would pause, maybe pretend to think about it, and, yeah, even get a few answers wrong on purpose.
Okay, so Turing has laid out the test, and he's defended it from his future critics. But how on earth would you actually build something that could pass it? Well, his approach was to think not about programming a finished mind, but about growing one. And his idea here was just so ahead of its time. He said, look, trying to program a fully formed adult mind from scratch with all its biases and knowledge, that's just too hard. It's the wrong way to go. He said the real path forward is to build a child machine, something simple, and then teach it.
This is just mind-blowing because he's basically sketching out the playbook for modern machine learning decades and decades before it was a thing. He talks about a child program with a basic structure and a bunch of blank sheets that would learn through punishments and rewards. I mean, that is literally the core idea behind reinforcement learning today. It's just wild.
Now, it's important to remember, when Turing was saying machine, he wasn't imagining some sort of sci-fi robot. He was talking about something very specific, the brand new technology of his time, the digital computer. And he breaks it down into three basic parts. You've got the store, which is basically memory, the executive unit, which does the actual calculations, and the control, which makes sure everything happens in the right order. And that fundamental model, memory, processing, and control, is still at the heart of the computer or phone you're using right now. Okay, so all of this builds up to the paper's incredible finale, where Turing stops just theorizing and makes a bold, concrete prediction about the future. And you have to remember the context here. We're talking 1950. One of the very first real computers had only been up and running for, 2 years. It was the absolute dawn of the computing age. And from that vantage point, Turing looked 50 years down the road. And this is what he said. He believed that by the year 2000, we'd be able to program computers to play his imitation game so well that an average person, after 5 minutes of asking questions, would have no more than a 70% chance of getting it right. Just let that sink in. He's not just saying machines will be smart. He's predicting a 30% failure rate for the human judge. This wasn't some vague sci-fi fantasy. It was a real, testable hypothesis with a deadline and a clear number to hit. And that, of course, brings us to right now. Turing, in his genius, sidestepped that messy philosophical debate about thinking and swapped it for imitating. But today, as we're all interacting with AIs that can write poetry, make art, and have conversations that feel shockingly human, we're forced to confront his question again. Was he right? Is the ultimate goal for AI just to be a perfect copy of us? Or are we seeing something totally new emerge, a different kind of intelligence that maybe the Turing test can't even begin to measure? That's the puzzle he left for us to solve.